Hi guys. So this is the lab for this week. It's based on the Bohr model of the atom, and so what you'll be doing is looking at a couple of different pictures of different gases. I've got hydrogen, helium, neon, and mercury, I believe, that I've got pictures of. I'm looking at those gases through a diffraction grating. And what we can see is emission spectra that are the result of the light that's given off by those gases coming through a diffraction grating. And that is what we will draw in these boxes right here. So I want to take a look just at the emission spectrum from hydrogen. So let me pull that up real quick. Okay. All right, so hopefully we can see this, and we've got right there, we've got the hydrogen tube itself, and we've got this thing inserted into a high voltage source so that we actually end up with a ton of energy across this tube. And as a result of that energy, some of the electrons in the hydrogen atoms get excited up into higher energy states. And then when they drop back down to lower energy states, they may emit light, or actually not may, they do emit light. By looking at this tube through a diffraction grating, so that's basically what I've done. I've got a diffraction grating that's held up to the lens of my camera, and then I'm taking a snapshot of that tube through that diffraction grating. What we can see off to the side here is the emission spectra of hydrogen. So we see a red stripe, looks like a, I don't know, turquoise, blue. Let's just stick with blue. Red, blue, and then a purple. So that's what we see for hydrogen. And so what I would do then here is I would go back to this, there we go. And I would fill in, and I'm going to do this one for you. This is the most important one to get right. This is the only one really that I'm gonna look at you cross-eyed if you don't get right. But I'm going to fill in my emission spectra for hydrogen. So what did I see there? I saw a red. I'm going to try and grab the colors. Maybe a blue. You notice I've got red right there, 750, and violet 400. I've got blue, maybe right in here, something like that. You guys don't have to color code yours, but I happen to have access to it here, so I'm going to go ahead and do it. And I've got the purple right there. And so that's what I would do for my emission spectrum for hydrogen. And here I can put, I'm just going to use there we go. Let's use my finger instead, H2. Okay, anyway. That's what I would do for my emission spectrum for hydrogen. Like I said, have pictures of the spectrum from helium, neon, and mercury as well. Okay, so that's the first part of the lab here. Before I discuss the second part of the lab, I want to briefly go over, I say briefly, I want to go over the Bohr model. So I'm going to pull up a little blank PowerPoint here so that I have something to write with. And let's do this. Well, let's try it. Sorry. There we go. That's nice. Okay. Okay. And so I'm going to go over the Bohr model real quick. So in the Bohr model, we'll look at it for hydrogen. We've got let's see, a nucleus, which for hydrogen is just a proton. And then we have all kinds of different orbitals around that nucleus in which the electron might reside. So, so far I've drawn 1, 2, 3, 4. I've drawn, okay, that's my 5th orbital. Okay. All right, so I've drawn orbitals number 1 through 5. So you know, my innermost one would be 1, my outermost one would be 5, and we represent those with our principal quantum number, which is n. So n equals 1, 2, 3, 4, and 5 for what I've got drawn in here. Now, let's say that I have an electron in my n equals 5 orbital. Okay, that is when it's sitting there, it's in an excited state. What it will do is it will drop down to lower energy states, and it may drop all the way from 5 to 1, or it could drop from 5 to 4, 5 to 3, 5 to 2. And then 2 to 1 or what have you, but there's all kinds of different transitions it could make. The one that I'm interested in for this particular discussion is if it were to drop from the n equals 5 orbital to the n equals 3 orbital. Okay, so we're going to use that idea that this thing maybe drops from the n equals 5. Whoops, that is not the color that I wanted. We're going to say that it initially is in the n equals 5 orbital and that it drops to the n equals 3 orbital. Now, when it does this, when it drops from 5 to 3, it is losing energy, and that energy doesn't just disappear. What happens instead is that some light is given off. That's the spectra that we were looking at in that picture. So some light is given off. Okay. It would be nice if we had a quantitative relationship here between our final and initial orbitals and the light that's given off. We do actually have this relationship. It's on the very top of your lab. This is our Rydberg equation. It says that 1 over the wavelength of this light is equal to z squared times the Rydberg constant times 1 over n final squared minus 1 over n initial squared. All right. Now that z there, that's the atomic number of our particular item that we're looking at. For hydrogen, z is equal to 1. So, and that's all we'll be doing in this exercise as far as computations go. So wherever you see a z when you're doing computations in this exercise, z's 1. R is the Rydberg constant. That is also given to you on the lab. And the Rydberg constant has a value of 1.097 times 10 to the 7 inverse meters. All right. So what we can do now is if we know that the final orbital, or the orbital that this electron drops into, and we know the initial, we can just plug in our values into our Rydberg equation and figure out the wavelength of the light that's given off. So let's go ahead and do that. 1 over lambda is equal to 1 squared times our Rydberg constant inverse meters times 1 over 3 squared minus 1 over 5 squared. All right, and if we go ahead and we work that out, we get that 1 over lambda is 7.8. That's supposed to be a 7. Let's erase that and start over. How about that? 7.801 times 7.801 times 10 to the, let's see here, 5 inverse meters. Well, that's great and all, but that's not actually what the wavelength of my light is. In order to get the wavelength, I would have to take the reciprocal of that, right? I want what lambda is, not 1 over not what 1 over lambda is. So when I take the reciprocal of this, I get that lambda is equal to 1.282 times 10 to the -6 meters. All right, so that would be the wavelength of the light that's emitted. Okay, maybe I don't want to stop there. Maybe I want to figure out, well, what's the energy of this light? There's an equation absolutely that I can use for that, that once again is given to you on your lab worksheet. Let me try and transition over to the next slide, maybe. Okay. That equation is that the energy of the emitted light is equal to H times F. That H is what's called Planck's constant. Planck's constant has a value of 6.26 times 10 to the -34 joules dot seconds. All right. And F is frequency. Okay. So we've got the wavelength of the light, and this equation uses frequency. Well, I'll remind you guys that when we were dealing with waves earlier on in the class, that we said that the speed of a wave is equal to its wavelength times its frequency. That's great. Let's see. So in this case, whoops, I don't know what, wrong button. In this case, the speed that we're dealing with is the speed of light. We represent the speed of light with its own special constant, or its own special symbol. That symbol is c. And the speed of light is 3 times 10 to the 8th meters per second. That's how fast light goes. All right, so we could figure out the frequency here if we divided the speed of light by the wavelength. 3 times 10 to the 8th meters per second. And our wavelength was, let's see here, with 1.282 times 10 to the -6 meters. And when we work that out, we get a frequency of 2.34 times 10 to the 14 hertz. Okay. And now we could calculate the energy of our light that's emitted. And we get out what? We get out 1.551 times 10 to the -19 joules. That's -19. All right. So that's our answer there for the energy of the light. It's 1.551 times 10 to the -19 joules. Now that's great and all, but that's a that's a what's that? No, that's a number that maybe we could use a different system of units to get a number that's a little easier to work with. All right, so I'm going to introduce a new energy, a new unit for energy. That unit is the electron volt, the EV, and there is 1 EV for every 1.6 times 10 to the -19 joules. So we could take our energy that we calculated and multiply it by this conversion factor. To get the energy of our light in electron volts instead. And so we get 0.969 EV. All right, awesome. So this is, let's see, this was briefly the Bohr model and what happens when we have electrons transition from a higher energy state to a lower energy state inside that Bohr model. Light is emitted. So I want to pull up real quickly the lab again. If I can find it in my list of stuff. There it is. Okay, there we go. This first exercise was is you guys looking at the pictures that I have posted and then drawing in the spectrum. The only one that I'm really concerned about that you get right is hydrogen. That is one that absolutely, if you don't do that one correctly, I'm going to knock off some points. The other ones, just use your best interpretation of the pictures you see. This is difficult. Even when we're in lab, actually, because you know that there's light everywhere, but just do your best with that. So for the second exercise, you're using this this equation that's up on the top of the page to figure out the longest and shortest wavelengths that could be emitted for the hydrogen Lyman transitions. Well, what the heck does that mean? The Lyman series is a result of electrons dropping down from a higher energy state down to the n=1 level. So you see this sentence right here. It says for the Lyman, Balmer, Paschen, and Brackett series in finals 1, 2, 3, and 4 respectively. For this first computational exercise, we're figuring out the longest and shortest possible wavelengths we could have emitted from an electron dropping down from a higher orbital to the n=1 orbital. And you'll have to think about what that higher orbital would be for the shortest and longest wavelengths. Here's a hint. These two paragraphs right here are really useful information. This kind of tells you what to do for the shortest and longest. All right, so for the first computational exercise is for the Lyman series, the next one's for the Balmer, the next one's for the Paschen, and then you're going to figure out, well, based on those three computational exercises that I just did, which one of those is responsible for visible light? And I'll give you guys a hint. If you don't know this yet, visible light occurs between, what is it right here, between 400 and 750 nanometers. That'd be 400 times 10 to the -9 and 750 times 10 to the -9 meters. So if you see something in the Lyman, the Balmer, or the Paschen that's inside that interval, that's probably says that that particular series is responsible for the visible part of the spectrum. All right, and then for this last one, we're figuring out the we're calculating the wavelengths for the 4 to 2 transition and 5 to 2 transition. This is where our initial is 4 and our final is 2, and we're figuring out lambda for that. And our initial is 5 and our lambda is 2, and we're figuring out our lambda for that. And then based on that information and the information that you filled out above this particular exercise, you can figure out what transitions are responsible for the red, blue, and violet lines that we see in the hydrogen spectrum. So that's what I'm asking you to fill out here for the red line. What's our N initial and what's our N final? For the teal line, what's the N initial, what's the N final? And for the violet line, what's N initial and what's N final? And then also figure out the energy of the emitted light, which I went through that example previously, and give that to me both in joules and in electron volts. All right, I have talked plenty. Hopefully I recorded this. Hey, awesome, I did. If you have questions, let me know.